This video is going to be about a specific form of the first law of thermodynamics for a system that has a bulk flow, but also is deforming to some extent. So what I'm going to do is kind of manipulate an expression that I derived in a previous video on enthalpy, manipulate that for a specific problem type, actually suited towards an application that I'm going to talk about in a second here. So on the right-hand side, I have all the mathematics behind this particular manipulation of the first law. But first, let's talk about the application that we're going to be dealing with here. So if we consider we have some kind of fuel tank and we need to expel the fluid or the fuel from this tank using a pressurized gas, this is actually a great example of a problem where we have both bulk mass transfer into our control volume or system, and also, depending on the way that we draw our control volume, it can actually be deforming. So first of all, for a system like this, we may ultimately want to ask, well, what is the minimum required amount of pressurant gas upstream that's required to push all of this liquid downstream to some process? And I actually have just drawn some other small components in here that may make our lives easier analytically, but also are somewhat practical. So initially, you would have some kind of isolation valve down here before the process begins, and the liquid is likely going to be nearly filled to the top. So that's going to be some kind of initial condition for us. And then also we've got a component between this high pressure gas tank and our fuel tank called a pressure regulator that's going to do nothing more than maintain the pressure downstream of this tank and downstream of this piping, all at the constant, at some constant pressure that we're going to set. And you could do this in real life with different types of regulator valves. So initially we'd open this valve, there would begin to have some kind of flow, and then everything downstream of this regulator is going to be a constant pressure. And we'll see in a moment why that makes life easy for us. Now, one thing to think about here is that when the gas is actually acting on this liquid, we can actually translate that into kind of a piston cylinder type of problem. So what I've done is looked at the CV2, or my control volume 2, where I've cut through the pipe in the top of the tank, and then also the way I've drawn it, it's matched against the walls of the fuel tank, but I haven't drawn an arrow here, and I probably should to make it a little bit more clear, but we're going to assume that the bottom portion of the control volume is going to move as the liquid level moves. So it's going to move with that interface. And the only constraint is going to be once we reach the bottom of the tank down here. So that's very similar to, say, a piston cylinder type problem where we have some kind of inflow, so at the top of the tank, and then the liquid we can just model as a piston, which may have some resistance or something that we can model like that. So we would be going from state 1 to state 2 in a piston cylinder assembly, and there could be an outlet fluid that's setting the resistance downstream, and we're ultimately interested in what happens to the fluid that's contained within our deformable control volume during this process, during this expulsion process. So moving over to the right-hand side, what I have up here, again, this looks pretty fancy. It doesn't really look like our typical form of the first law, du equals del q plus or minus del w. But it really is. It's just in disguise. So if we neglect this integral outside and the dt down there and just look at what's in brackets, really that's the first law. And if you're unfamiliar with this, please see the video on the derivation of enthalpy and its use with open systems with the first law of thermodynamics. So in brackets here, we've got two terms on the left-hand side and 1, 2, 3, 4 terms on the right-hand side. And I'm going to go through each of these one by one just to explain exactly what they are, what they mean. The first term is going to be the time rate change of internal energy within our selected control volume. Okay, and the second term is going to be the net flux of internal energy into and out of our control volume. Now, if you looked at the previous video, these two terms actually came about from switching a reference frame. And prior to these, in the enthalpy video, we had just a single term that we were able to break into two. And it was actually, there was a time derivative outside of an integral. And so we were taking a derivative of a deformable control volume. So we could actually replace these two terms here with that single time rate change of the total internal energy of our deformable control volume that contains the same particles. But since we're going to have some flow into or possibly out of our control volume for this example, we want to use this approach here where it allows us to express our flows into and out of the system as an internal energy flux. But just to be clear, the previous formulation where we only had one term on this side, that's typically used when we have either a fixed volume or a fixed mass of particles that we're following around. It's called the Lagrangian approach. And then when we use the Leibniz rule, again, you can refer back to the video on enthalpy, to break up that integral into two terms, we've now kind of transitioned into what's called an Eulerian approach. So we have, say, a fixed volume in space, and we're allowing fluid to flow through it. And this is just the same thing. These two terms mathematically are equivalent to the single term, but we've just changed the way that we're looking at the problem a little bit. So again, time rate change of energy within our selected control volume and the net flux of internal energy with respect to the control volume. And things get a little bit more familiar over here. We've got the total rate at which energy is added by heat into the control volume. I've got the total rate of shaft work that's interacting with the control volume. And now we've got two more terms over here. Again, these were explained initially in the video on enthalpy, but I'll explain them again in this video as well. So what we can do is evaluate work that's associated with a fluid flow into or out of the control volume. You can imagine fluid upstream of, say, this tank, or even in this problem here, the fluid that's flowing into our purple control volume actually has to do a little bit of work in order to flow. So it itself and all the upstream fluid is acting as a piston in order to push fluid into the control volume, and vice versa if we were considering an outflow. So this is what we call boundary work or pressure work, flow work. There's a number of different ways that we can describe it. But it is the energy required by a fluid to displace adjacent fluid when it's moving into our control volume. And it comes into being by simply just the product of pressure and a displaced volume. And this has the units of energy. And this is essentially what this is right here. Again, this is the pressure acting at the boundary of our control volume. There could be a number of discrete locations. I'll get into that in a minute. This is, say, the velocity of the fluid at that interface. Let me skip over this term for a second. This n sub I is just a unit normal vector in order to describe the orientation or geometry of our surface, and this is a differential surface area element. Now, in this particular term, I've just multiplied by a ratio density over density, so it's unity, and so I haven't really modified things here, but I would like to distinguish between these two terms, okay? They look essentially exactly the same, especially if you neglect this blue term here, which is unity. They are the same. But what I'm doing is I'm saying, okay, maybe on my surface I have some discrete spots where flow is coming in, and I'm going to account for those in this integral. That's why I put a subscript flux here. Now, this guy I am going to associate with a deformable portion of my control volume. This is how I'm going to model how the control volume interacts with the surroundings by pushing on the surroundings, but with a moving boundary rather than flow crossing the boundary. So they're equivalent types of boundary work, okay? But you may want to actually discriminate a little bit more and say, this is boundary work associated with a deforming control volume, whereas this is boundary or flow work associated with a flux of fluid into the control volume. So in this particular example, especially in control volume 2, we're going to have both. And so we need to retain both of these expressions. Now, some of the side notes here that I've mentioned up top is going to make it easier for us when I integrate with respect to time this entire equation, because really I just want to look at the end state and the initial state and find things like the total amount of heat transfer, total amount of work, etc. So before I do that, if we look at just this, these three terms in the middle right here, these three variables, rho, v, and u. So again, density, so average velocity, or the velocity of the fluid at that point, and then the internal energy, specific internal energy. The product of these three is just going to give me the specific internal energy times this expression here. So I've got dm dot ds. And really all this is saying is that rho v itself can be thought of as a differential amount of mass flow per unit surface area. So a differential mass flux. And what we're doing is summing up this differential mass flux over the entire control volume surface. And a similar way of thinking can be looked at over here. Because I've multiplied by rho over rho, I can rearrange this. I'll take P over rho as its own little term, and then I've got rho VI. Now, rho VI, like I talked about over here, is really just a mass flux, and inside this integral, I can think of it as a differential amount of mass flow rate per unit area, so dm dot ds, okay? And then finally, over here, where I haven't manipulated the term by multiplying it by unity, I can just take the P alone and then look at velocity itself is really a volumetric flow rate per unit area. So I'll look at this guy or rewrite it as dv dot ds, okay? And so if you multiply these new expressions out, it simplifies things a little bit. And what I'll do is, we'll talk about that in a second when I move to the second line. So what I'm going to do is just take this entire equation, integrate it with respect to time, and we'll look at each term individually. So the first term, I'll take the integral with respect to time of the time rate change of internal energy within the control volume. So if I rewrite this guy, actually, and I should have written it up top here, rho u is actually just the internal energy per unit volume within our control volume. So I'm taking the time rate change of the internal energy per unit volume and then integrating that over the entire volume. So I could look at this expression right here as the second derivative of the total internal energy, capital U, with respect to volume and time. Or this guy right here, I can just look at it as du dv. Okay, so again, just a differential amount of internal energy per unit volume. And then I'm taking a time derivative of that, which gives me a second derivative. Then I'm bringing my dv down, and then also integrating this whole thing with respect to time. So you see my dv's cancel, my dt's cancel, and then I'm left with really just du, okay? And then capital U itself, the total internal energy can be broken apart into little m times little u, or the mass times the specific internal energy. And that little, so dmu can be integrated, and you arrive at simply just the mass times the specific internal energy of the control volume at state 2, minus the mass times the specific internal energy of the control volume at state 1. Okay, so this ugly looking expression has simplified down into two nice things that we can calculate pretty readily once we get down to it, after I've integrated with respect to time. As far as the next term goes, and actually, yeah, it's this guy, the second term right here. If I multiply this by ds, I have u dm dot, okay? And if I assume that there's only fluxes not across the entire boundary, not a continuous diffusion flux across the whole thing, but discrete fluxes at different points, so pipes or tubes entering or leaving the control volume, this integral turns into a summation. So I'm going to say there's j discrete points on the control volume where fluid is either entering or leaving. And so this u dm dot really just turns into a summation, okay, of m dots, j's, and uj's at each discrete point on the surface. And then I'm integrating this with respect to time. And at each point at each discrete point on the surface, I'm going to assume that the internal energy is actually steady, so it's not a function of time, and it's also uniform over the entire cross section of that inflow or outflow. And if I perform this, it's really, so the U can come out of everything. And the summation can come out as well. So it's really just dt times m. And if you integrate a mass flow coming in or out, it's really going to be what was the total amount of mass associated with that pipe or tube coming in or out during that time interval. And then we still have the summation out front and then the internal energy associated with that same flow. So this entire flux term comes into a discrete amount of terms. So summation over J, inflows or outflows of the mass associated with that, that flow over the entire time of integration times the internal energy associated with that flow. So these are discrete internal energy fluxes. Now moving on to, I'm going to skip these guys. These are pretty trivial. If I integrate these rates with respect to time, I just get the total amount of heat transfer or the total shaft work, or if there's other exotic forms of work, I'm integrating a rate with respect to time, so I'll get the total amount of energy associated with these processes. So these are pretty trivial. Moving on to this guy, over here it looks very similar to the top one. If I multiply, or the one above it, if I multiply the DS's, they cancel, and I've got P over rho, the M dot, okay? And so I'm summing up these mass flows associated with each discrete point or surface J. And so the P over rho is also going to be associated with the same J's where the internal energy was coming into the system. So the internal energy fluxes, but the fluid also has a pressure and a density associated with it. And so again, this is the work done by the flowing fluid into or out of the system, whereas this term is the energy carried by that same fluid. So that's why I've got the same subscript J. And same procedure here, keeping the minus sign in mind. I've got a summation over those same J points of the total mass associated with those flows over the time interval of interest times the quantity P over rho associated with that flow. And just realize, and actually, I mean, you'll see it over here, but I wouldn't jump to this expression just quite yet. But if we move this term to the left-hand side of the equation, and you look at these two guys, so this is the term here on the left-hand side, this is what I can move over. What I'll end up having is the sum over all these discrete inflows and outflows of mj total times uj plus p over rho j, okay? And this you should recognize as the definition of enthalpy. So what we'll have is the total enthalpy flux associated with all of the discrete inflows and outflows. Now finally, this last term here, which we associated with a deformable control volume, I'm going to assume that it's only deforming at a single point, okay? And just akin to this problem here, where we've just got this lower boundary that's moving. So a single surface with no flux through it. Like I mentioned before, we can rewrite this expression as just minus P times dV dot ds. Multiplying the ds's, they cancel. We've got minus P dV dot. And that comes over here. I forgot a minus sign. But, so I've got the integral over time, okay? And I didn't have a summation here because I assumed it was only occurring in one location. Although you have to realize that this pressure that we're talking about in this particular portion of the analysis is actually going to be felt throughout the entire control volume. So we're going to have to handle that in some way. But anyway, at one single point, so we've got minus P dV dt, same thing as V dot, and integrating that with respect to time. So the dt's cancel, and we've got the integral of minus P dV. Now, what I've done is said, you know what? Let's neglect any pressure dependence on the volume of our system. Okay, and this is actually a pretty big assumption. It only works this particular analysis right here. So I'm saying P is just P2 plus P1 over 2. So if we have a system at some pressure, it expands to another pressure, and the volume is changed, I'm going to say that this integral simplifies into minus the average pressure during that process times the delta V during that process, so PdV. So I've pulled out the P. So only if we're undergoing a linear process, or P is linear in V, Or if we have a constant pressure, does this actually work? Okay, if we have a more complex evolution of pressure with volume, then we're going to actually need to perform the integral of P of V dV. But for the types of problems that you'll likely encounter in this course, this should be good enough. So take the average pressure times the total change in the control volume. Now, if we combine all of these terms together and really just rearrange a little bit, we should get this term right here, mu at state 2. So the total energy of the system at state 2, so the mass times the specific internal energy at state 2 minus the total energy at state 1, internal energy, so the mass times the specific internal energy at state 1, plus the sum over all the discrete locations where we have inflows and outflows of the total mass associated with that discrete inflow or outflow over the time of interest, okay, times the enthalpy associated with the flow. And we've assumed, again, that that was not an unsteady process, that the enthalpy flowing in or flowing out was going to be constant with time and also constant over the entire cross-sectional area. All right, so we just have this H, which could be pulled out. Actually, not pulled out, but again, Hj is going to be a constant associated with each particular inflow or outflow. Then we've got the total amount of heat transfer, the total amount of shaft work or other types of work besides boundary work, and then finally the movable boundary work, so minus P times this P average times this delta V CV. So moving forward in the analysis, what we're going to do is apply this equation to this specific practical example over here, and hopefully be able to come up with an expression for the mass required in order to displace all of this liquid, depending on actually how we constrain the process in the tank up here. So the gas may be expanding adiabatically, isothermally, or in some other thermodynamic constraint, which will actually feed in to this next control volume. So that's going to actually influence the value of H in this problem here, and we'll see how that influences the overall mass requirement. Moving on with the analysis, I've recapped up here the end result of the previous section in the video, and what we have is the internal energy at the second thermodynamic state minus the internal energy at the first thermodynamic state, plus the sum of all of the enthalpy fluxes. I've changed one thing here. I've put a bar over the specific internal energy associated with the specific flux, just to signify that if there were some unsteadiness in that flow, say H were changing with time, or U, or the pressure, anything associated with this flux, we could just take some kind of average. So even if it was varying across the cross-section, although I said in the previous section that we would neglect any time changes or spatial changes in these variables, but just to be a little bit more kosher, I've put a bar over the top to signify that this would be an average quantity, so averaged over a period of time or averaged over a cross-section. So the total enthalpy flux, and this is equivalent on the right-hand side here to the total amount of heat transfer, the total amount of energy added to the system via shaft work, and then minus this boundary work term, so the average pressure of the system times the change in volume of the system. Okay, so this is working against the surroundings, or the surroundings working against the system. So what I want to do is take this general form of the first law for an open system with a deformable boundary and apply it to this more specific example over here, which I've listed up top. So it's propellant tank pressurization expulsion. So I mentioned before that this lower half of our setup here, so downstream of the pressure regulator, we can model this as kind of a piston cylinder assembly with an inflow and then the bottom boundary of the control volume being movable. Now if we look at the upper purple control volume, CV1, we have a rigid volume with just one outflow. So what we need to do is manipulate this equation up top in order to reflect the specific configurations in control volume 1 and 2. And so that's what I've done here. So for control volume 1, you can neglect, and CV2, you can neglect these terms I've crossed out and keep them down initially until I've explained why they're gone. But we've got the internal energy of the gas in the pressurant tank at state 2, minus the internal energy of the gas of the pressurant in the tank at state 1. Now I've got minus just one mg out hg bar. So this term right here is going to represent all of the mass of pressurant that's left the system over the time interval that we're considering, times the average specific enthalpy of the pressurant as it leaves the system. So we do have to realize here that, again, this is a constant volume tank, and we're expelling mass, so the energy in the tank is going to be dropping with time, so its pressure is going to be changing, temperature, etc. So we would expect that the outflow of enthalpy to be changing as well. But we're going to take some intelligent average between the initial state and the final state, and that's what I've signified here. And again, minus sign because it's an outflow. Now on the right-hand side, the only thing that I've included is the possibility of heat transfer into this tank. And I've neglected shaft work. We don't have any shafts entering or leaving. And because it's rigid, there is no movable or deformable boundary work. This will come into play a little bit later. Like I've listed over here, I said maybe there's some waste heat. For a particular example, in a rocket propulsion system, some of the pressurant gas is heated prior to being sent to the pressurant tank, or maybe the tank is heated at some point or even downstream of the tank. And so this adds a little bit more energy to the gas that it may give up during the expansion process and in expelling the liquid from the actual fuel tank. So this will come into play later. Now as far as the second control volume, we have the internal energy of the gas at state 2. Okay, and state 2 would be when this control volume over here is fully flush with the entire fuel tank volume. Okay, well, what I'll mention in a minute, well, actually I can mention it now. Initially, we'll assume that this CV is just kind of a line or just a plane, so there's no mass inside of it, and eventually it expands all the way until it's hit the bottom of this tank. Okay, so that's going to have some implications on our initial and final conditions. So the final condition here, the final internal energy of the gas, when the control volume coincides with the entire tank volume, and this would be minus the internal energy of the gas initially. Okay, so we can say that there's nothing in there initially, so we can cross it out. There's nothing. Plus, now during the course of the time that we're concerned with, there is going to be an inflow of gas from the pipe that's connected to the tank, which is downstream of the regulator. And this is going to have the same energetic value as the gas that's leaving the pressurant system. So it's just at the interface between control volume 1 and 2. So this quantity right here, which represents the total enthalpy flowed into the system, is the same magnitude as the total enthalpy that flowed out of CV1. Okay? And on the right-hand side over here, neglected the possibility of heat transfer, although it depends on the application. No shaft work, not for this particular configuration. But because our bottom boundary is moving and the control volume is deformable, the gas is doing work on the liquid downstream and whatever resistance may be placed on the liquid. So this term P bar, or minus P bar delta V, has some significance, all right? And this P bar in this particular example would be the pressure that the regulator is set at, and the delta V, in our case, because we chose the initial control volume to be infinitesimally small, and then the final state is coinciding with the tank, this delta V is nothing more than the tank volume itself for the fuel. So at this point, what we would attempt to do, and actually let me backtrack one second. I've crossed out this term here because I'm assuming that all of the mass of the gas in the pressurant tank is expelled, okay, at the end of our process. And this isn't quite practical because if we had nothing in that tank, we'd be pulling vacuum in the tank, and if that were the case, the pressure in this side of the system may be lower than the downstream side, and we wouldn't get any flow in the proper direction. But for the purpose of just showing you the steps of this problem, I've assumed that we have nothing left. So there's no energy left in that pressurant tank. All of that mass has been expelled and leaves this system and goes down to the tank system. Okay, that makes things a little bit easier. So what we can do is either attempt to manipulate these two equations together to form one expression and try to calculate how much mass is necessary for this expulsion process. Or what we could have done, and we'll actually get the same result, is draw a different control volume. We could draw one control volume that completely bypasses this regulator system and includes the tank and then the bottom down here, this movable boundary. And what you're going to see in a second is that really we get the same result doing that way, which is slightly simpler, or combining these two equations. So looking at this term right here, the third term in both CV1 and CV2 energy conservation equations, because they're of the same magnitude, I can simply add these two equations together, same magnitude, different sign, and I come up with another expression here. And what I get is M1, and I'm able to factor this out because if you look at this term right here, this is the mass of the pressurant gas initially in the pressurant tank at its initial energy, okay? So that's going to be all of the mass that's contained in the problem altogether. And then here, at the end of this expulsion process, all of that same pressurant gas is going to be in the tank. So it's the same mass of gas, but it's at the internal energy associated with state 2. Now, just as an aside over here, this is written out in a little bit more detail. I didn't go over the mass conservation aspect of this problem because you should be able to do this off the top of your head at this point. But if you want to see it explicitly, it's written out on the side over here. So we have this required pressurant mass, or the total mass of pressurant, times the difference in internal energy between the gas at state 2 when it's fully occupying just the tank, or the fuel tank, minus the internal energy of the gas at state 1 when it's occupying just the pressurant tank, okay? And this is equivalent to the total amount of heat transfer into the pressurant tank, minus the total amount of work associated with expelling that liquid, that fluid. So just doing some algebra to manipulate things here, we can solve for M1, which is the required pressurant mass, and we get P bar times V tank minus Q total divided by the internal energy of the gas initially, minus the internal energy of the gas at its final state. And I've just rearranged the signs a little bit to make things a bit more clear. So I just changed the signs here and changed the signs here and divided. But what this signifies here is a positive quantity. P bar and V are both positive quantities. P bar, again, is the pressure that's set downstream the regulator. It's going to be a positive quantity. V tank is going to be a positive quantity. If we just look at this, the magnitude of this is going to be larger if we're operating at higher pressures, or if we have a larger tank. And it makes sense that if we have more liquid to expel at a higher pressure, it's going to take a bit more energy to do so, and hence more mass. The heat transfer term I'll come back to in a second. If we're working with an ideal gas, I can assume that the difference in internal energy between the initial state and the final state can be related to the temperatures through the specific heat capacity at constant volume. So I break this up into CV times T1 minus T2. Again, looking at the magnitude of the numerator here, if there is positive heat transfer into the system, what we get is that this difference is going to be smaller. So we're requiring less mass. And that makes sense, is that what we're doing is essentially using possibly some waste heat to help relax this energy requirement for expelling the fluid. So not only do we have the energy initially contained in that pressurant tank in order to do work on the liquid and expel it out of the fuel tank, but also we're getting a little help from some external energy source. Another thing to look at too is that the larger this delta T is, the larger the value or the magnitude of the denominator, and obviously the smaller this quantity would be. And what that would signify, a large delta T would mean a large energy difference, and even without heat transfer, it would mean that the gas gave up quite a bit of its energy in doing work on the liquid or the fuel. And the larger that energy difference, the less mass is required. One more thing to think about too, and it's not quite captured in this analysis, we haven't included a functionality between these temperatures and then the pressure here. Now, it's a good thought experiment. You could pause the video now to think about what would happen if we did link these two, and possibly go back and make this link for yourselves. But two things. If the temperature is lower in the tank, the gas is going to want to shrink a little bit. Its volume is going to change and be reduced. And so the pressure in the tank is going to drop. And as the regulator upstream senses that, it's going to want to send more mass into the tank in order to get the pressure back up to its nominal set point value. And so this is going to actually increase the mass requirement. So we do have a non-linearity here that we really haven't captured in this simple analysis. Additionally, and I should have mentioned it over here, if there's heat transfer out of the system, so if there's some kind of loss of energy, that is going to increase our demand for pressurant, moving in actually the opposite direction. We would like to minimize this. So again, recapping, there's a lot of information in this equation here, from just a simple energy conservation analysis for a pretty practical problem. And if you get a chance, you can go back and incorporate a few more details into this to get even more insight.
The Teaching Center, UF's Learning Resource Center.